how is it gonna work when you have multiple execution threads simultaneously? So far we've been thinking in terms of one thread, but what if you have several? So remember, all the threads share one and the same object heap, but each thread has its own local variables. So it could be that the virtual machine is the one controlling the execution of these execution threads, and it may be that maybe there is a processor core, so some of these threads can be executed in parallel, so you don't know. So your Java program is supposed to run in any possible computer, so even with those that have a single processor only. So how it works, thinking of this kind of old-timey model of a single processor concurrency, that of all these threads, so one was the main thread, but it's nothing special, it just happened to be created first, but other than that, the main thread doesn't have any special powers that the other threads would not have. And the virtual machine, because it can only do one thing at a time. So how it works is that one of these threads at any given time is active. So that's the one that the virtual machine reads the next bytecode instruction and executes it. So simulates the effect of the bytecode instruction in the object heap and the local variable stack, and then moves on to the next instruction, which normally is the next one in the memory. But if the current instruction is some kind of a conditional or unconditional jump, so then the instruction has the effect of jumping to that part of the machine code. So now it's important to realize that the threads in the Java level, notice that you cannot affect this in any way. So which is the currently active thread, and how many instructions is the virtual machine gonna execute it before it decides to make a context switch. So context switch means in this situation that the virtual machine decides, alright, the current thread has now been executed enough, and now it's somebody else's turn to get a turn, and then the virtual machine switches to execute some other thread from the place where it previously left off. And this happens not after every instructions, because the context switch is a relatively expensive operation, but still the context switches in a modern computer, they happen so rapidly that from a slow human eye it looks like all these threads are executing truly in parallel. So just like in a movie, we're too slow to tell apart the individual image frames. So this idea that the thread, the virtual machine decides how far each thread is gonna be executed before somebody else gets a turn. So this is now known as preemptive multitasking. So this is the way for if we go one level lower. So your operating system, the processes there are in the same role as the threads are there inside this Java virtual machine process, and then this idea that the operating system decides how much each process is executed. So if some process gets stuck in an infinite loop, so contrasting this to what is called the co-operative multitasking, meaning that each execution thread or process at the operating system level would be executed until it voluntarily gives up its turn. So this in general is just not it's just difficult. First of all, you're writing some complicated nested loop logic, so how do you know when you're gonna give up a turn, so that you don't accidentally do something that is takes much longer than you expected? And what if some thread is a bug, gets stuck in an infinite loop, or gets stuck waiting, asking for a input from a human who is attention is elsewhere, and humans are slow anyway. So cooperative multitasking, well, it does have its role. I've been raving about it in the 109 Python. So how can I say it otherwise? That in Python, so this idea of coroutines, so it doesn't, it's not there under that name, but we saw it already. We called it the generator. So generator object is like a separate execution thread, but it doesn't get automatically execution time So the fact that somebody tells the generator, give me your next element, so then the control switches to the that generator thread, so to speak, is not a thread, but like in this analogy. And then, so when the generator voluntarily gives up its turn by calling yield, so then the context switch happens and the execution continues from the other thread. So the thread is the wrong term here, but it's just the analogy. So coroutines, cooperative multitasking have a place. It just we gotta know where that place is. So these generators, so this is the great illustration now, that instead of trying to do everything in one sequential execution, that we split the execution into conceptually separate pieces, so that these pieces are simpler and easier to understand separately of each other. And then the good generators can be reused there, so that X is like we take an execution thread and not a thread again, but you know what I mean. So then terminology here. So when it's operating system, we talk about the processes, and then the Java virtual machine is one of the processes, and it simulates an imaginary computer inside it that has threads inside them, and then those threads are divvy up the execution time. So why do we use one word in operating system and one word in Java? So the difference, if I've understood it correctly, again, so it's been 2 decades since I took these courses myself, but the threads, that they share memory, whereas processes are shielded, that neither by accident or malice, so one process cannot change the data in another process. So then whatever communication the processes wish to do, they have to do it through the operating system services, then in a disciplined and secure manner. So let's that we get to the first example and see this in action. So let's look at how threads work in Java. So this Java, one of the first of these major languages where this kind of concurrency was part of the language from day one. And actually, so how this Java, now that our goal is to be thinking high-level ideas, high-level abstractions, and leave the low-level nitty-gritty decisions to the compiler and the virtual machine. So even though the threads are there in the standard library and the language, so doing that way, so like a Java 1 way from the 90s, this is too low-level thinking, so it doesn't mesh with our other idea of trying to express ideas in high level of abstraction. So if we do this, have to do this low-level operations, the concurrency control ourselves. So we're gonna be using what was introduced in Java 5. So Java 5 was a big improvement, Java util concurrent, so high-level concurrency abstractions. I'm gonna be using those in all my examples. Now this low-level, now you can to create the threads on your own, but this is managing your own threads in a complicated system is again too low-level thinking. But just so to see how this works, we're gonna be doing it, but then later we're gonna be solving the problems with the higher level abstractions. So objects of the class thread, these are special in the Java virtual machine. These objects represent the execution threads that exist in your virtual machine. And these are so tightly married to each other, so the thread inside the language and then the actual underlying thread things that are executing the language, that in Java virtual machine, so you just create an object of the type thread, and the virtual machine creates an execution thread for that object. So the thread objects and the actual threads are always one-to-one. So now this also follows, would it make any sense to take a thread object and save it to a file and then email it to all-time email, so somebody else, and then because the thread doesn't represent anything that exists in their computer. So these threads are a very special class in Java. They're very close, like they're underneath the language at the same time as they are in it. Been reading too much Alan Watts again, I see. But okay, so back to the actual thing. So you create a thread, and that's it. It starts running. So that's how easy it is. So is concurrency that easy? No, because synchronization. But launching threads, so far we're still in the fun and the simple part. But then, to make this more fun, like the main thread always starts at the static main method. But when you create a new thread, well, does that also start from the main method? So now you have to make your main method a giant switching yard, like for trains, that every new thread somehow finds out who it is and where is it supposed to go from this main central switching yard. So that implementing that kind of logic, so that eliminates all the conceptual advantages of concurrency. So what happens instead is that you determine where exactly is your thread starting to run by giving it an object that has a run method. So the fact that the object has a run method, the fact that it's guaranteed at the compile time, is the fact that your class implements the interface runnable. So the class, the objects represent the task that the thread is executing. So the object typically contains the data that the task needs to execute. But the run method is just the starting point of the execution thread, and just like the execution can escape from the main method to any other part of the program, so theoretically, so whatever you do in the run method, so the execution goes wherever it goes. So think of the run as the main method of the new thread that you created. The thread settings, there is some that you can set, like is it the daemon or not. Thread priorities, these are only for optimization. Concurrent program must be correct for any priorities. Priorities are just a wish, and they have no real power to guarantee that some thread is gonna be faster than another one. So you can set this to optimize, but just like with any optimization, the principle that don't optimize the system until it's correct and working. So optimizing something that doesn't work is always a waste of time. So then you tell the method, the thread object, tell it to start, and then it makes a top level call to the run method of the runnable object that you gave it, and it keeps going wherever it goes from there. And should the execution return from your top level run call, so that's when the Java virtual machine terminates the thread. The thread object still continues to exist as long as you have live references to it, but the underlying thread is gone. So if you want more execution, you have to create a new thread yourself. But now, as I said, as we'll see, this creating the threads yourself, this is too low level thinking, so there is a utilities for that. And then this concurrency over the next couple of weeks is gonna be a great illustration that we're climbing up from the low level language to the higher level abstractions. So then when we program with the Java computation stream, that's a different thing than the data streams. So then we don't even think about the threads at all. So we're just gonna be expressing the computation in such a high level form that they can be automatically parallelized.